I'm Andy Lankford. I'm from the University of California, Irvine, and I'm one of the two deputy spokespersons of the ATLAS experiment. Well, we got much more data in 2011 than we expected, and it's enabled us to narrow down the allowable region for the Higgs boson considerably. We've now been able to, with the amount of data we have, surpass the results of the Tevatron. And together with CMS, during the fall, we excluded a much wider region. Now each experiment individually can exclude a region similar to that with the data available, narrowing down the allowable region for the Higgs boson to a range of very roughly approximately 115 GeV to about 130 GeV. This just happens to be the region that was favored by previous experiments. If there is a Higgs boson, it would most likely be in this region. And it's also the region that's most difficult for us to explore, because in that region the Higgs decays in a way that's a little bit more challenging for us to detect. One of the properties of the Higgs boson is that it gives other particles mass, and as a result, it gives it the property of the way it decays depends on what its mass is. If the Higgs were to have a high mass, it would decay in one fashion to vector bosons, for instance, W's and Z's. And if it's in a low mass, in the region that's presently allowable, it only decays into more difficult to detect and less frequent decays, such as into a pair of photons, Higgs decaying into a pair of photons, or perhaps Higgs into two Z particles, vector bosons, but at a much lower rate. And those bosons then we detect decaying into leptons. So it would be a Higgs into 4 leptons, and that has a very rare process. Very nice signature, but a very rare process. Well, we've largely, those are very important channels in the design of the ATLAS detector. So for instance, in our electromagnetic calorimeter, it was designed in such a way not only to measure the energies of the photons and the locations of the photons, but also the directions of the photons. And that property is very important for us to know where the photons were created, and therefore to be able to use the photons to determine the mass of the Higgs. And again, one of the things that's very nice about this decay mode is that we have a very good resolution, precise resolution for measuring the mass of the Higgs, and so it gives us a very strong signature. Once we detect enough of the Higgs particles, all with similar mass, we'll know that we have a real signal. But it demands a lot of data in order to get that many pairs of photon decays at the right mass, because the photons can be produced by many different standard model processes too. Tens of thousands of photons pairs produced for every 10 Higgs decays.
So when would you expect?
We need a considerable amount more data than we have now. It'll probably take all of 2012. Perhaps if things go well on the summertime, but we would really like to have 4 times as much data as we have now in order to study this region in detail. At the same time, we'll be improving our analyses, trying to make ourselves more sensitive. But it's really more data that we need the most. So it will be summertime at the earliest that we can say really anything more definitive than we can right now with all the 2011 data. Right now, each of the experiments is concentrating on completing the analyses we have now and bringing these to publications early in the new year. So we'll not be doing a combination before those publications.